All right, this is a continuation in a series on land navigation. Now, if portions of this video are at all unclear, I would recommend that you go back and review part 2. Again, while the point of this series is to produce a very complete overview, it still is not a substitute for real hands-on training. Always seek safe hands-on land navigation training from a capable instructor. Okay, let's jump right on in. Recall that in part 2 we talked about place values and how to minimize unneeded place value denominations, and how we turn this cluttered coordinate into this. We then learned how to construct and plot 4, 6, and 8-digit grid coordinates. We likewise understand that each of these coordinate types signifies a focus of measurement. What I mean by that is a 4-digit grid coordinate will measure an area of 1 kilometer square, a 6-digit grid coordinate will measure an area of 100 meters square, and an 8-digit grid coordinate will measure an area of 10 meters square. Let's now talk about representative fraction. We've been mentioning different map scales all throughout this series, but we haven't really zeroed in on what it means. Let's do that now. Well, it's very simple, and to demonstrate, I'll use a 1 to 24,000 scale map. So here's a question. Just where can we find a map's representative fraction or scale? Right, in the bottom center, right here. Now, for this example, I'll randomly use units of inches. So 1 to 24,000 just means that 1 inch on the map equals 24,000 inches on the ground. And just to give you an idea of how far that is, 24,000 inches is equal to 609 meters or 2,000 feet. Now let's take a 1 to 25,000 scale map, which is very popular in the military. Once again, 1 inch on the map equals 25,000 inches on the ground, and 25,000 inches is equal to 635 meters. But realize this, because it's a little more encompassing than that. A map's representative fraction is really a unitless ratio. And what does that mean? Well, that means that one of anything as it is drawn to scale on this map is in real life on the ground 24,000 times bigger. For example, the size of this particular building as it is drawn to scale on this map is 24,000 times bigger on the ground. Or if you want to calculate it in the other direction, on the map, an object is 1/24,000th its original size. You get the pattern. Okay, we now understand map scale. Great. But what about this over here in the upper right-hand corner? What does 7.5 minute mean? Okay, let's tackle that. Well, 7.5 minutes has to do with map size. And what I'm going to do here is begin my explanation of map size by starting off with a map covering a lot of area. We'll subdivide this area, and as we go, we'll eventually get down to a 7.5 minute map. Okay, here's a chunk of land that is 1 degree latitude by 2 degrees longitude. Now, what does that mean? Well, at its simplest, we know that 1 degree equals 69 miles or 111 kilometers. So 2 degrees over here would be 138 miles or 222 kilometers. And here is our 1 degree latitude by 2 degrees longitude map. Now note the scale or representative fraction at the bottom center. It's 1 to 250,000. That means we're covering a lot of area, but we're also doing so by sacrificing a lot of detail in exchange. So just how much area does a map of this size cover? Well, we know that United States Geological Survey maps in this size cover 4,580 to 8,669 square miles. So this here is a map that covers a lot of area. So it's a very good overview map of a regional area. Now let's take that same 1 by 2 degree and subdivide it into quarters. Okay, good. Now, in this configuration, one of these quarters measures 30 minutes latitude by 1 degree longitude. Now, note that I said 30 minutes and not a half degree. That's because degrees are properly subdivided into minutes. 1 degree contains 60 minutes. In addition, 1 degree is commonly measured in quarter chunks. So here's 15 minutes, 30 minutes, 45 minutes, and finally 60 minutes, or a full 1 degree. And since we know that 1 degree is equal to 60 minutes, a half degree, if you will, is equal to 30 minutes. We also can convert this 1 degree over here to 60 minutes as well. So there you go. Let's take a look at a 30-minute by 60-minute map. And here it is. Do you notice the increased detail? Now, the size of the map is noted in the upper right-hand corner, and this is indeed a 30 by 60 minute series topographic map. And the scale found at the bottom is 1 to 100,000. We're still covering a good deal of area, but we're also retaining a good deal of detail as well, as you can see here. This is a very good compromise, and this size of map is very popular for a general overview of a given area. In fact, you can expect coverage from about 1,568 to 2,240 square miles. Now, let's take this 30-minute by 60-minute area and subdivide it even further. In fact, we're going to subdivide it into 15 by 15-minute squares. Now, let's take one of these 15-minute grids and see it on a map. And here it is. Again, we can check the size in the upper right-hand corner, and this is indeed a 15-minute series topographic map. And again, the scale is found at the bottom center, and it is a 1 to 62,500. Now, please note here that this size of map has been phased out by the United States Geological Survey, but you can still find older prints online. Now, we see here that a 15-minute map is covering a smaller area, but it's also retaining a greater amount of detail as well. And this size covers on average about 197 to 282 square miles. Now, guess what we're going to do now? You got it. We're going to subdivide this 15 by 50 minute area further into 4 more quarters. The result is a 7.5 minute by 7.5 minute map. And since a 7.5 minute map is created from 4 quadrants of the old 15-minute map, they are often referred to as quadrangles. Once again, we can check the size in the upper right-hand corner, and it is indeed a 7.5 minute quadrangle. Once again, the scale is at the bottom center, and it is 1 to 24,000. And you can see the detail is remarkable. This particular map here is a hybrid aerial topographic map. Pretty neat. And this is why for a foot patrol especially, the 7.5 minute quad is very popular. And on average, a 7.5 minute quad will cover 49 to 70 square miles. So there you have it. You have the 7.5 minute quad, good for up close and personal work on the ground. You also have the 30 by 60 minute map, good for a broader view of your surrounding counties. And finally, your 1 by 2 degree map, which is good for a grand overall view of your entire regional area. Let's now talk about areas of operation. Let's say that I'm right here at this point. As a baseline, I myself would procure 7.5 minute quads, not only for my location here, but for all the surrounding quadrangles as well. And you can do that by looking down at the lower right-hand corner of your quadrangle. This center quad here will be your actual map. And as you can see, you'll be able to easily locate the names of all the surrounding quads as well. It may be a little expensive, but trust me, it's a few bucks well spent. And that being said, to these 7.5 minute quads, I would most definitely add a few 30 by 60 minute maps as well. Why? Think about it. A 7.5 minute quad covers on average a width of roughly 8.5 miles or 16 kilometers. Now, if I'm in an SUV and the highways are clear, I can fly across a 7.5 minute map in 15 minutes, 30 minutes tops. And if I were in a plane, forget about it. It'd take me a couple of minutes. So whether you're in an SUV or plane, having only 7.5 minute quads will have you constantly switching to the next quadrangle over and over again as you move across a large area. Better to have a small scale map like the 30 by 60 minute here. This way, it won't necessitate so many switchovers from map to map as you move across a large area. And while we're on the topic, a 1 degree by 2 degree map would likewise be an excellent tool for an overall view of your entire regional area. Now, let's briefly pause here and very quickly touch on the Military Grid Reference System, or MGRS. For starters, know that the Military Grid Reference System is directly derived from the Universal Transverse Mercator Coordinate System, and we already talked about that in Part 1. In fact, the military adopted UTM as the basis of its map systems way back in 1947. However, the military uses a different labeling method. There are essentially three parts to the MGRS labeling scheme. The first is the UTM grid zone designator, and again, we already spoke of this in part 1. Recall that the entire globe was divided in this manner, by 6-degree longitudinal zones intersected by 8-degree latitudinal bands, as you see here. Remember that from part 1? And recall how we all fall into one of these UTM zones. Austin, Texas, for example, is in UTM grid zone 14 Romeo, and that's your grid zone designator. Okay, the military further subdivides these UTM zones into 100-kilometer grid squares, like this, and this is only an example. As you can see, Hawaii there in the middle of the Pacific Ocean. Here's the continuation of the 100-kilometer square identifiers over the U.S. southern states, and here's our target destination, Austin, Texas, which happens to be in the 100-kilometer square identifier Papa Uniform, or PU. Now notice that each 100-kilometer grid is given a 2-letter designator. One letter represents a specific column and the other a specific row. Now from here, it's just a matter of constructing the numerical part of the coordinate, just like we do in the civilian world. So let's go ahead and do that. Here's our target location. We're in Weberville, and our 4-digit grid coordinate is 42 easting by 45 northing, and that renders us this 1-kilometer grid square. Now, to find the 100-meter grid square, we need a UTM grid overlay, and we already went through this again in part 1. So let's count left to right. 0, 1, 2, 3, 4, 5, 6, which is our easting. And now our northing, 0, 1, 2, 3. And our upgraded 6-digit grid coordinate is 426 easting by 453 northing. And again, that renders us this 100-meter grid square. Now, taking this a step further, we can achieve a 10-meter accuracy, but we'll have to use a protractor. We start with a horizontal scale counting towards the left grid line. So counting from 60, 60, 61, 62, 63, 64. Now for the vertical scale, counting upwards until we reach our destination. 30, 31, 32, 33, 34, 35, 36, and 37. And this 8-digit grid coordinate gives us a 10-meter accuracy. Now, let's go ahead and quickly plot a grid azimuth. Let's start with our location here in Weberville, and our coordinate is already stated in the gold box above. Let's say that we're going over here to this fork in the river. We already know that we're in UTM grid zone 14 Romeo, and we also know that we're in the 100-kilometer square identifier Papa Uniform. From here, we merely construct the numerical coordinate. Our easting is 39 and our northing is 45, which renders us this 1-kilometer square grid. Here's the same 1-kilometer square grid close up. And to get accurate to a 10-meter square, we again break out the protractor. Now again, counting to the left grid line on the horizontal scale, we have 87. And on the vertical scale, our destination mark levels out at 83. With both our present location and destination clearly marked, we merely draw a pencil line connecting the dots. Now place the center of your protractor on your present location, making sure that it is precisely centered on the index mark, or the center crosshairs here. Make sure that 0 is pointed grid north, and that the index lines or center crosshairs are exactly parallel to the vertical and horizontal grid lines. Take your time. Now from here we can see that our grid azimuth is 280 degrees to our destination. And that's it. So let's recap. We used our protractor to measure precise subdivisions of a given grid square in order to plot our present location and to plot our destination. We then used the degree markings on the edge of the protractor to determine our correct azimuth. And in our case, we calculated a 280 degree grid azimuth. Now, if we were actually going to move out and travel to this destination, we would need to complete one more very important mathematical conversion using the MAPS declination diagram. But we'll save that for part 4. Okay, folks, that's all for now. Stay tuned for part 4 when we discuss the following topics in depth: declination diagram, terrain features and topographic map symbols, a quick overview of the lensatic compass, and how to determine your pace count. This is Analytical Survival saying, stay safe, my brothers and sisters.